Nice sunny day out today. Okay, there we go. So we left off somewhere around here, and we said, well, how are we going to make the compound in C by reductive amination? Just so, in the interest of real estate here, I'm just going to delete this, what I had in the previous video. So I'll just delete that, and we'll give C a shot here. So if we made the disconnection where I have the red bond broken, okay, if we were to do that, retrosynthesis would look something like this. So we would have the nitrogen, we'd have a secondary amine like this. And then if we count carefully, if we count 1, 2, 3, 4, 5, 6, and then the nitrogen. So let me do that. So we have 1, 2, 3, 4, 5, 6, and then the so 4, 5, 6. So let me just number these 1, 2, 3, 4, 5, 6. And then our aldehyde would be out here like this. So we would tie those together to make the ring. So all we would need is this as our starting material. And of course, we would treat it with a catalytic amount of acid and sodium cyanoborohydride. Okay, now if we made the blue disconnection, all right, well, in that case, we would have our carbonyl. Maybe I'll draw this in blue. Our carbonyl would be out here like that. And then we'd have 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5. Oh, I'm doing wrong here. 1, 2, 3, 4, 5, 6. No, that's right. 1, 2, 3, 4, 5, 6. And then we would have our primary amine like this. And then we would use the exact same conditions. So a catalytic amount of acid and sodium cyanoborohydride. And either way, that is going to give you the product, right? We're not going to do the last one right now, but you can take a look at that in the solutions manual. And if you have any questions about that one, feel free to fire away. All right. Let me see here. Oh, I see. I made a mistake here. I put an extra bond. There we go. So for the one on the top, I drew a methyl group on there. I wasn't looking carefully, so that should be an NH2 group. So that should be a primary amine on both of these. Okay, there we go. Fixed it. Let's move on to the next one. So it says come up with a structure of methamphetamine. Well, I kind of gave that away earlier today, but you should be able to figure it out here. If we take phenylacetone, which is this compound, and then we treat that with methylamine, so CH3NH2, the catalytic amount of acid, and sodium cyanoborohydride, that will give you methamphetamine, or methamphetamine. Oops. Which looks like this. So now we've got this, we've got our nitrogen over here, and there we go. So now you've made methamphetamine. All right, and let's try a couple more here. So we've covered the synthesis strategies for making a primary amine using Gabriel synthesis, azide synthesis, and reductive amination. And then we said once you've made a primary amine, you can keep going with more and more reductive aminations, then finally an alkylation to make a quaternary ammonium ion. And so it says using ammonia as your only source of nitrogen, show how you would prepare each of the following amines. Well, you would do successive reductive aminations to make the compound in A. It's kind of one after the other. So one of them you would add so here you would use, acetaldehyde, right? And for this part over here, okay, you would use this aldehyde. So there we go. Which would look like this. So those are the two aldehydes that you would need to make the compound. So you would just do it in two successive reductive aminations. So you'd start with acetaldehyde like this, treat it with a catalytic amount of acid and sodium cyanoborohydride. So sodium cyanoborohydride. And you would use ammonia as your amine. And that would give you ethylamine. And then once you have ethylamine, you would treat that with this aldehyde. So this aldehyde here. And you would do the exact same conditions. So H plus and sodium cyanoborohydride. and that will give you the desired product. All right, if you wanted to do B, that one's even faster. Okay, we'll just make some space down here. If you wanted to do B, for that one, all you would need is cyclopentanone. Right? If you start with cyclopentanone and treat that with ammonia, catalytic amount of acid, and sodium cyanoborohydride, that will give you cyclopentanamine or cyclopentylamine. They both mean the exact same thing. All right, and I'll leave you to give C a try. So for that one, you would use 2 equivalents of formaldehyde for these and cyclopentanone for this part of the molecule here. There we go. So now we're going to get into a new section which deals with the acylation of amines. And again, like I told you before the last break, acylation of amines is something that we covered already, right? We said that if you took acetyl chloride or acetyl chloride, depending on your pronunciation, so acetyl chloride, which is an acid chloride, and treated it with excess of primary, secondary amine or ammonia, you end up with an amide, right? So here we're starting with a primary amine, so we end up with a secondary amide, NaHCl, and we said you need 2 moles of the amine are required. Why is that? It's because the second mole of the amine is going to react with HCl, right? It's going to react with that, and they're going to combine, and you're going to end up with the alkyl ammonium chloride salt, right? So it neutralizes the HCl that's formed in the reaction. So we covered this again in chapter 20. So there's nothing new on this slide. So you might be wondering, well, why is it shown in this chapter? I guess it is in the amines chapter. Well, what we're going to do is we're going to use it as a protecting group. But before we do that, I want to help you recall a reaction that we looked at earlier on. We said way back in chapter 18 that if you took aniline and you tried to treat that with bromine, instead of just brominating at the para position, which is what we assumed, right? We made that assumption that you could make this compound. You actually wouldn't get that in real life because the amino group is so activating, right? This is an electron donating group, and so you get polybromination. So you brominate at the 2, 3, and 5 positions, right? 2, 4, and 6 positions. 2, 4, 6. Tribromoaniline is what you would end up with. And again, it's because the amino group is such a powerful activating group. So how do we mitigate the activity of the amino group? Well, the answer is we acylate it. So if you acylate it, then you have an amide. So you go from a really strong activator to a moderate activator. And once you have that moderate activator, right, which moderates the electron donating capabilities of the nitrogen, because you have an electron withdrawing group on here, that means that if you treat it with bromine, you only get bromination in the para position, and then you can just hydrolyze the amide bond using sodium hydroxide or strong acid. It says the disadvantage to this synthesis is that the amide hydrolysis requires harsh conditions. One thing I should point out is that something that's missing on this slide is that you can do the reaction with just sodium hydroxide, but if you did it with aqueous acid, that would give you the aryl ammonium ion, and so you would have to do a second step. So it would be 1 H3O plus, and then 2 would be mild base at least, just to do the deprotonation. Okay, so that's something you want to keep in mind there. Now, aromatic amines do not undergo Friedel-Crafts chemistry. And the reason why is that when we do Friedel-Crafts chemistry is that they end up getting protonated, they react as a Lewis base. And what that does, they react as a Lewis base with our Lewis acid. So this is our Lewis acid, this is our Lewis base. That's what I was trying to say. And what that does is it deactivates the ring. And so you can't do a Friedel-Crafts. And so you're probably wondering, well, why is this in the acylation section? Why? Because if we acylate it, right, then we can do a Friedel-Crafts. Because once we acylate the nitrogen, then it's not going to react as a Lewis base, right? We know that the lone pair on this nitrogen is not basic because it's participating in resonance. So we can do a Friedel-Crafts alkylation, no problem. Okay, and then we can just hydrolyze it either in base or 2-step process, 1 step, or first step H3O plus, second step sodium hydroxide in a two-step fashion like this. So there you go. So with all that in mind, let's see if we can tackle a problem here. It says, when aniline is treated with a mixture of sulfuric acid and nitric acid. So this is what they're saying. I'll write it down here in red. If you take aniline and you treat it with sulfuric acid and nitric acid. So this is the conditions for nitration, okay? The expected nitration product, so you would expect that you would get paranitroaniline, okay? So you would think, I'll get this compound, but in fact, you don't get it. And the reason why you do not get this compound is because when you treat aniline with a strong acid, you actually end up protonating the aniline to make an anilinium. So you end up with the conjugate acid of aniline. And when it's protonated, the resulting ammonium group is a meta-director, right? So it's going to direct to the meta position instead. So the question is, how would we make this compound? Is there a way to make that compound? And of course, we can make that compound, but we're going to have to use a protecting group. So let me just move this kind of out of the way, okay? And this is how we're going to do it. We're going to take our aniline molecule, and we're going to acylate it. So once we acylate it, so we'll treat it with acetyl chloride, okay, and we end up with our acyl group. And now it's still an orthopara director, but now it's not going to get protonated because the lone pair on the amide is not basic. So now we can treat it with sulfuric acid and nitric acid together and make the paranitro. So we've got our nitro installed here. And then we have our amide up here, okay, like that. And now all we have to do is hydrolyze the amide. So I'm just going to choose base since it's a one-step procedure, and that will give you para-nitroaniline. So para-nitroaniline, just like that. All right, so a little bit of a protection. So this is our protection step, protection. And this is our deprotection step. All right, and this is our nitration. Nitration. Okay, so with all that in mind, let's take a look at this question. It says, starting with nitrobenzene and using any other reagents of your choice, outline a synthesis of parachloroaniline. So for starting with nitrobenzene, okay, we're taking nitrobenzene, and somehow we want to end up with parachloroaniline. Parachloroaniline. All right, but we know that we can't just take aniline and chlorinate it, right? Because if we take aniline and chlorinate it, we're going to put chlorines in positions 2, 4, and 6. So that means we have to do the acylation. So that means that in terms of a retrosynthesis, we're going to have to make this compound. We have to make the N-acyl aniline. So how do we make that compound? Well, the first step is going to be reduction of our nitro group. There's several ways to do that. I'm just going to put HCl and zinc, and we heat that up, and that's going to reduce the nitro, but you're going to get an anilinium ion, the NH3 plus ion, so we have to treat that with base, base in the second step, and that's going to give us aniline. So there's our aniline molecule. Next thing we're going to do is we're going to acylate it. So we'll treat it with acetyl chloride, and that gives us the acyl group, like so. There we go. Now we can do our chlorination. So I'll use chlorine, iron 3 chloride, and that's going to install the chlorine para to the amide, like this. And then the last step, we just hydrolyze it with sodium hydroxide, and we're done. So again, it's a protection, deprotection scheme that we have to use here in order to make this compound. All right, let's take a look at a couple more reactions, and then we'll probably call it a day after that. So next, we're going to cover what's called Hofmann elimination. And I know you know all about Hofmann and Zaitsev. We covered that way back in Chapter 7 of Organic Chemistry 1, but I want to give you some more details about what Hofmann elimination originally was. So it says, like alcohols, amines can serve as precursors in the synthesis of an alkene. So we know that if we take an alcohol and if you heat it up in strong acid, you're going to make the alkene. So you could just do H2SO4 and heat, and that's going to drive water up. Or you could do a tosylate, treat it with tosyl chloride and pyridine, and then you could treat it with a hindered base. I mean, not in this, yeah, I guess you treat it with a hindered base, like T-butoxide or something like that, okay? But how do we do it with an amine, okay? And the way that we do it with an amine is we proceed through a quaternary ammonium ion. So we end up passing through something that looks like this, where we end up with a positive charge on our nitrogen, and then we end up doing an elimination. So the idea is always to convert a bad leaving group into a good leaving group. And I told you that if you have an amine and you treat it with iodomethane, it will do what's called exhaustive alkylation. And you would convert the amino group into a trimethylammonium ion, which is going to be a good leaving group. So now all you have to do is an elimination. You have to pull off a beta proton. So you have a base, or I'll just put here base like that, which is going to pull off this proton, and you're going to lose the leaving group like this while you form the double bond simultaneously. The thing is, the base that's used is not things like DBU, DBN, T-butoxide, sodium methoxide, sodium hydroxide. The base that we use, the only time this ever comes up in this class, is silver oxide. So silver oxide is the base that we use, and there's a good reason for that. It's because you end up forming silver iodide as a precipitate, and I'll talk about that maybe more next class. But anyhow, silver iodide precipitates out of the reaction mixture, and it helps drive the reaction forward is what it does. So you need silver oxide and water. Actually, yeah, maybe I can explain it here. So what's going to happen here is once you do the exhaustive alkylation, you're going to end up with this, okay, like that. All right, and then you're going to have the iodide salt. So then what happens when you have the silver oxide in there is that you end up swapping the iodide. There we go. I'll just draw it like this. You end up swapping the iodide for a hydroxide ion like that, and then you precipitate silver iodide out of the solution. So since you form a solid here, that is going to precipitate, and it drives the reaction forward based off of Le Chatelier's principle. So the base that actually removes the proton in the end is a hydroxide ion. So that's why it's drawn like that here. And we call this a Hofmann elimination. Now, of course, we have two types of beta protons. We have the one in black that's being shown being abstracted, and then we also have the ones in blue. Now, why do we get the less substituted alkene in a Hofmann elimination, right? Less substituted alkene in a Hofmann. You know that from way back in Organic 1. Well, now you're going to see why, and it's really based off of nothing more than a gauche interaction. So if you take a look at the elimination, that would form the more substituted alkene, or the Zaitsev, right? This would be the Zaitsev alkene. And you look at the, look down this carbon 2-3 bond here, you see that we have a gauche interaction between the R group and the methylated nitrogen. Whereas if we do the Hofmann elimination, form the less substituted alkene, so Hofmann, in that case, we don't have that gauche interaction, so no gauche interaction. I'm not going to ask you to draw this, this Newman projection or anything, or you might have to know that it's a gauche interaction that prevents the Zaitsev from being formed, but that would be about it. Okay, I'm not going to make you draw the mechanism, or the mechanism, yes, I think you should know a little bit about the mechanism, but not have to draw the Newman projection. I don't remember ever asking students to do that. So it says here, draw the major product that is expected when each of the following compounds is treated with excess methyl iodide, followed by aqueous silver oxide and heat. So if we take cyclohexylamine, which is this compound here, we treat it with excess methyl iodide, that is going to give us this compound. All right, so now that we have this compound, we're going to treat that with silver oxide. So silver oxide in water, and we're going to heat that up. And there's only one type of beta proton in this molecule. So the only thing that we could end up with in this case would be cyclohexene. In the next compound, R3-methyl-2-butanamine, if we draw the structure of that compound, it looks like this. Oops, it's a chiral center. So I'll draw it like this. There. So is this R? So we go as yes, this is the right compound. So after we treat this with excess iodomethane, and then in the second step with silver oxide, water, and cook it up, okay, I can either abstract the red proton or the blue proton. Could anybody tell me which proton I'd pull off? Would it be the red one or the blue one? Yeah, thanks, Audrey. Absolutely, it's the red one, isn't it? So I would end up with the Hoffman product, the Hoffman alkene. There we go. The next section deals with reactions with nitrous acid. So nitrous acid, and after we cover those, I teach you the nitrosonium ion. We talk about N-nitrosamines, which are carcinogens, and then we talk about diazonium salts and diazotization. And then I don't ask you that mechanism, but we use the diazonium salts to do what are called Sandmeyer reactions. And after Sandmeyer, we learn the Schemann reaction and azo coupling. And that's really the end of the chapter, okay? And we have the whole class devoted to this chapter on Wednesday. So what I think is we'll end it here for today. And then on Wednesday afternoon, we'll finish up the chapter, which won't take all that long. And then we can spend the rest of the class doing practice problems.